So Florence grew up in Malaysia, in the town of Muar, a small fishing village of roughly 3,000 people. That's located off the Straits of Malacca. As a child, she always had an aptitude for mathematics and science, and was particularly interested in space as she grew up watching Star Trek reruns. She was accepted to and attended the University of Maryland College Park and earned her Bachelor's of Science degree in Electrical Engineering. And she then went on to attend Johns Hopkins University, where she got her Master's of Science in Electrical Engineering and her Master of Business Administration, graduating with highest honors. She now works at NASA Goddard Flight Center, where she has played an active role in development of mass spectrometers for 8 space missions to various places in the solar system. And she is the recipient of numerous awards for her work as a civil servant and as a member of Goddard's Women Advisory Committee in the 90s. She had a ringside view of Goddard's strong support of women's rights when we built the first lactation rooms here at Goddard. She has been an active advocate for women in science, in technology, engineering, and math careers, which have historically been male-dominated fields, and she often speaks to the public about her work, including giving the commencement speech at the University of Maryland. With those few remarks, ladies and gentlemen, help me welcome our speaker, Florence.
Thank you. Thank you for inviting me, and to Claire for suggesting, and Charles for inviting me here today. I'm standing here to talk about my journey in the U.S. as an immigrant, an engineer, a woman working at NASA. I grew up in Malaysia, a third-generation Malaysian Chinese. Contrary to my looks, I am not from China. My hometown is Muar, Johor, and it's got no traffic lights when I was growing up. The town had mostly bullock carts and rickshaws, scooters, bicycles, and the occasional cars. My parents said that when they were teaching in the school in the 60s, there were about 1 to 2 cars in the parking lot. This is the occasion of my parents' engagement and the results of their marriage. I am the middle child, and my brother, who's the younger one, wasn't born yet. So there's only 3 of them. Most houses in my village had no plumbing, no indoor plumbing, and even when they did, it had no modern toilets. Sorry, can't quite drive. My grandfather's and grandmother's bathroom was an outhouse. It was used by 2 households, 16 people, until 1976, when I was in 6th grade, when they upgraded to a squat toilet. Because I spent a lot of time with my grandparents, I'm used to that configuration. Growing up, we had a black and white TV, and programs came on only between 5 and midnight. I saw sporadic reruns of Star Trek, as Charles mentioned, and I was absolutely fascinated by space. I owe my success to my parents. They made sure we had access to books. Mom could borrow 4 books at a time from the library. My sister and I got 2 books every week. And we would trade with each other. She would get 2 books, I'd get 2 books, and we would say then we could read 4 books a week. So we had one room in the local library. It had 4 shelves of books with probably 1,000 books. I'm pretty amazed that I can borrow up to 50 books at a time at my local library. And we have 4 library cards at home, which means I could borrow 200 books at once. So this is pretty amazing, since our little library in my hometown had only 1,000 books, 5 weeks of borrowings here. My father grew up farming and fishing. He was one of 13 children. His father died when he was 2. My mother was the oldest of 7, the only girl. After World War II, both of them went through teacher training to become school teachers. In those days, you didn't need to go to college to be a school teacher. College-trained teachers are paid twice as much as teachers who are trained in the teachers' college, like my parents. My parents watched their students, fresh graduates from colleges, come back to their school and teach with no experience and immediately make twice as much as they did. My parents told me, work hard, go to college. We don't have college degrees. You must go to college. You must. My siblings and I are the first of our generation in our family to graduate from college. On May 13, 1969, we Malaysians call it 513, race riots broke out in Kuala Lumpur between the ethnic Chinese and the ethnic Malays. Relations between the two groups had been tense for over a decade. The Chinese were generally wealthier and more urban, and the Malays were generally poorer and lived in rural areas. Many people died that day and the subsequent days. To this day, the number of dead is still unknown. The authorities painted the faces of the dead black to prevent identification based on race after the riots, according to my mom. After 513, the government introduced the new economic policy, an affirmative action policy for the majority native Malays that limits non-Malays races to access to education, to housing, to government contracts, etc. The goal was to eradicate Malay poverty, but the policy was very controversial because it focused exclusively on race, religion, and not economic need. Most of the Malays are Muslims. Malaysia also had a law to put away dissenters called the Internal Security Act, ISA, which was originally enacted to imprison communists in the 50s by Malaya's British colonial rulers. Under ISA, the government could arrest you, imprison you without charge, and hold you for 60 days, and renew that indefinitely in the interest of national security. Over time, this rule, or its current guise, has been used to put away dissenters. And today, the law still exists. My parents, wishing to protect us, and they exhorted us, do not discuss race, religion, politics. We would stay quiet. Do not rock the boat. Do not inflame tensions. For as long as I could remember, my parents and my family whispered fearfully about the riot and the unjust implementation of the new economic policy. We didn't speak out in public because we were afraid of being blacklisted or arrested under ISA, or worse, the community suffered another 513. I watched my parents bite their tongues for my entire childhood. In the early 70s, the Malaysian government founded the Mara Junior Science Colleges, a series of residential schools, high schools, modeled after the Bronx Schools of Science, with the goal of alleviating poverty, restructuring society, and growing a well-educated workforce to usher Malaysia into the ranks of developed nations. These schools were co-ed and had better facilities than the public schools, smaller size class sizes, and better qualified college graduates as teachers. The government identified the brightest kids to populate these schools. I was lucky enough to be admitted to such a school 300 miles away from my home when I was 12 years old, and I stayed there for 5 years. I was one of 20 non-Malays in a school of about 580 students. The population of Malaysia at the time was 60% Malay and 40% non-Malay. Our school admitted 96% Malays and 4% non-Malays, somewhat in line with the new economic policy. There was no doubt I and others like me enjoyed a good education at the school. However, there was ever-present religious and racial tension between the Malays and non-Malays, resulting in intimidation and bullying of the minorities. One non-Malay boy told me he had urine poured over him while he slept at 3 a.m. because he refused to throw a physics test, that is to deliberately do poorly so as to lower the class average. His locker was broken into multiple times. In more than one occasion, Malay boys would spit at me and menace me with misogynistic or racial epithets while I walked to school. I had rocks thrown at me. Where then were the teachers? How was it that they did not prevent such bullying? Some teachers didn't know. Some teachers were complicit in their attitudes. They were openly disparaging of the non-Malay kids, and we non-Malay kids knew who. The Malay students learned from these teachers, and those students made life miserable for the non-Malay kids. And they were reinforced by their teachers' attitudes. To be fair, there were also Malay bullying, but we non-Malays felt our race keenly. Our diversity was not celebrated. Instead, we were made to feel lesser. There wasn't a defined anti-bullying policy in the school. Society had to say, bullying is not okay. Even in the US, it is only in recent decades that the anti-bullying message has come out. The boarding school environment was the crucible that formed me. During these 5 years, something in me stiffened. I grew determination. Some non-Malay students not able to withstand the pressure left. I and others like me stayed. I looked forward to the promise of being given a place at university. Even though I was a non-Malay, as a Mara Junior Science College student, I had the chance to land a spot in the Powerball lottery of educational opportunity, and I did. The Malaysian government offered me a loan to study in the US, and I leapt at it. I believe that I was one of the few and last non-Malay students to receive such an offer. Despite Malaysia's institutionalized racism policies, I'm always grateful to the Malaysian government for giving me that opportunity at the college and for my loan. I am one of the lucky few. While applying for college, I wanted to study aeronautical engineering. Instead of being encouraged, my counselor told me, major in accounting, because I was good at math, which was more acceptable career path for a girl. I made a counter proposal, a non-gender specific major at the time, computer science, and the counselor signed off on my application. When I got to the US, I changed my major to computer engineering. In 1982, I experienced my very first plane ride from Kuala Lumpur to Kalamazoo, Michigan. The journey took some 33 hours with all my connections. That trip pretty much cured me of the allure of flying. That was my very first plane trip. I came here with a burning desire to succeed. I quickly learned American English was slightly different from British English that we learned in Malaysia. Early on in the search for erasers, I asked a bookstore clerk for rubbers. It isn't rubbers, it's erasers. I still say torch instead of flashlight, dustbins instead of trash cans, and so on. Here are all the different English, British, American words. Throughout college, I worked at least 20 hours per week while taking 15 to 19 credit hours per semester while maintaining a 3.5 cumulative GPA. By the time my younger brothers came to US 2 years later, in 1984, I had saved $6,000, enough for out-of-state tuition for one child for 3 semesters. It was still expensive at the time because my parents only made $700 in total a month. My parents and my older sister, who had graduated earlier, were also sending money to support my brothers at University of Maryland. We all knew the way to a better life for the entire family was through a good education. My brothers also graduated from University of Maryland in electrical engineering. My parents are remarkable people. They taught us to love and care for one another. In the US, I met Americans and other international students with diverse opinions. For the first time, I learned about real equality and meritocracy. I was delighted to be accepted and to be judged by what I knew, and not by my race, my religion, or by my politics. What a wonderful place America is. I could speak up without fear and would not be blacklisted or arrested for my views. Not everyone I met was nice to me. When I spoke up at a doctor's office to protest my surrender of my social security number, I met a woman who said to me, "You people think you can come here and do what you want." And once at a party, when I remarked to a man about that the Patriot Act was similar to the Malaysia's Internal Security Act, his response was, "If you don't like it here, why don't you get the F out of here?" Well, happily, people like these were in the minority. I grew to love it here, and in 2001, I became a US citizen. In 1985, I got a job as an intern working San Marco data in the laboratory for planetary atmospheres, hired into Nelson Spencer's lab by a scientist named Larry Wharton. I got the job through networking via a friend of mine. My job interview question was, derive Maxwell's equations. So I did. I got the job. Don't ask me how to do it now. The origins of Goddard's Planetary Environment Laboratory, that's the name today, code 699, harken back to the founding of Goddard Space Flight Center. Nelson Spencer, the guy there in the top left-hand corner, came to Goddard through University of Michigan's Space Physics Research Lab in the 60s. And by the 60s, he was leading the Laboratory for Atmospheric and Biological Sciences branch. The scientists studied terrestrial aeronomy and radiation effects. In the 40s, when Spence was at SPRL, the Space Physics Research Lab, he built the first instruments and launched them using captured V2 rockets. At the time, everything was so new, and many, many rockets blew up. V2s could carry 2,000-pound warheads, and they didn't have enough instruments that weighed 2,000 pounds. So they had to make forms for where their instruments and their 6-volt car batteries go, and they filled the rest of the shell with melted lead as ballast. I learned this while I was doing the research for the history of this branch. It was interesting. Here's a picture of Spence with V2 rockets, and this is the V2 rockets, and this is them working on some experiment. And this is a very, very young Dan Harpold and Spence again working on one of the first mass spectrometers that were launched in the 70s. I am proud to be part of this group that traces its beginnings to a pioneer of space exploration. And this is the history of the lab, as you can see, in the 60s, and we're somewhere between the space science and, I guess, earth sciences, since we launched mass spectrometers to the planets. By the mid-80s, when I was hired, our lab, at the time named Laboratory for Planetary Atmospheres, had launched instruments to study Earth's atmosphere on dynamic explorer missions, 12 San Marco missions, Pioneer Venus Orbiter, and Galileo mission to Jupiter. After my graduation, Hasso Niemann, at the time the second chief of this lab, hired me to work on the Pioneer Venus ONMS data under Wayne Kasperzak. Stanway, who was a senior manager, saw I wasn't doing real engineering. I was just doing data analysis, he thought, and introduced me to Charlie Ehrman in the Laboratory for High Energy Astrophysics, or code 660, so I could be properly mentored by electrical engineers. I got a job designing electronics and writing assembly code for the wind instruments and moved to Building 2, where code 660 was, under Frank McDonald in 1987, and later Steve Holt. While in Building 2, and code 660, I met my future husband, Tom Nolan. Immediately after we met, he left to go to Australia for the GRIS balloon launch to investigate supernova AT7A. You may have heard Neil Garrels talk about the supernova 1987A in a previous Maniac talk. Tom and I communicated via the VAX 11780 phone utility, a very primitive instant messaging system, while he was in Australia. Tom had to dial in and hopped from computers from Alice Springs, then to Sydney, then to Stanford, then to Goddard. I had to be logged into the Goddard's computer real time, and we chat over a 14.4 baud phone line. We've always told our kids that their parents courted over instant message in 1987 at the dawn of the internet age. At Lear Laboratory for High Energy Astrophysics, that I learned to design electronics and write code, and I learned much from the brilliant engineers of Code 660 in Building 2. In 1991, I went back to work for Hasso-Niemann to build electronics for Cassini INMS and GCMS instruments. At this time, I started working with Larry Frost, Eric Rahn, who's here in the audience, Ryan Miller, Ken Arnett, Steve Patel, John Maurer, etc. There's a lot of very brilliant engineers at the time that we started working together. And it was under Steve's and John's tutelage that I learned the business of designing spaceflight. Cassini and GCMS was an instrument on the Huygens probe to Titan. I was flabbergasted that ESA and NASA would spend such tremendous amount of effort and treasure into building a probe that would take 7.5 years to travel to Titan, then have the probe take data for 60 minutes, and then crash land. I was also petrified that I would fail at this job. Well, so I tested my hardware and software extremely thoroughly. When I first saw the picture of Titan after Huygens landed, I finally understood why the effort of building the probe was so well worth it. The first picture gave me goosebumps. It called to me. I don't know why, but it just did. This picture, this very picture, was the first picture of a moon other than ours, and I understood why I love working at NASA. The very idea that we humans have the smarts and the sophistication and the cooperation to build such complex hardware that can operate flawlessly after 8 years through the inhospitable environment of space is a testament to man's ingenuity and perseverance. It is a privilege to be part of this group. As a woman working at NASA Goddard Space Flight Center for 30 years, I've seen a lot of change. A few years before I started working in Building 2 in the 80s, it had no women's room. A men's room had to be converted into a woman's room. When I arrived, I had an office on the 3rd floor. I had to run down to the 1st floor to use the nearest restroom. This is a picture taken in Building 7 basement a few weeks ago. The signs haven't caught up yet. Thankfully, we have women's rooms on every floor of our buildings, albeit these ad hoc signs. In '94, when I was pregnant with my first child, I wanted to nurse. So I asked for a lactation room to express milk. I was told, no, this nursing thing was a temporary condition. After enduring the discomfort and non-hygienic conditions of using the restroom to pump my milk, I realized the need for a lactation room was not just about me. It was about others that came after me. I guess that was the I have to speak up moment. I was determined to do something about it. I joined the Women's Advisory Committee and we got to work. And one of the advisory members are here today, Ginny. After lots of PowerPoint presentations to a few women and many, many men, we managed to convince management to fund a pilot program. I planned and built the first lactation lab. Okay, only NASA. We call this a lab. Which actually had a name, says lab there, but I think they eventually took it out. They said lactation room. And with the approval of Dot Zucker, 5 years after my initial request, 5 years. It was a lot easier to have 2 babies, design, mass spectrometers, 3 of them, and build and launch them, nurse, and get a master's degree, than to get buy-in for a lactation room in the 90s. In time, Goddard and other agencies saw that lactation labs were actually good to have. I'm glad to report we have 16 such rooms on campus, and our recruiting brochures proclaim we're a family-friendly workplace with a lactation program. Yay! In 2006, Paul Mahaffey, who's then the lab chief after Hasso-Niemann, asked me to be the electrical lead engineer for SAM, Sample Analysis at Mars, an instrument on the Curiosity rover. While working on SAM, I had the privilege to work closely with Eric Rahn, who's here again, Dan Harpel, John Maurer, Steve Patel, Tom Nolan, Chris Johnson, Benny Pratt, Mike Barciniak, Bob Bob Arvey, Eric Linus, and others. SAM is possibly the most complex instrument flown onto the surface of a planet. This is SAM. It's the size of a microwave oven. And here is the SAM gas processing diagram. And this is SAM and I. SAM is an instrument with a quadruple mass spectrometer, a tunable laser spectrometer, a gas chromatograph from the French team, supported by a gas processing system with a sample manipulation system from Honeybee Robotics with 74 cups, 2 wide range pumps running at 100,000 RPM, 2 ovens that heat up to about 1,000 degrees, hydrocarbon traps with TECs, heaters, getters, helium gas reservoirs, 2,000 psi, 100 or so heaters in a network of sensors, scrubbers, etc. All good to the 10 to the minus 10 torr. It is a pretty complex instrument. We had to learn to work with multiple partners across the world and the country and with each other. We had terrible technical challenges. Some days felt like everything could go wrong, and everything did. For example, TLS developed myopia. I call it myopia because we couldn't focus it. The laser had become unfocused due to an indium gold interface. There were issues with that interface. And the people from Chris Webster and Greg Flesch came and worked nonstop for 2 weeks to refocus this laser. It was very, very difficult. The gas columns sprung a leak, the gas chromatograph. So how do you fix tubes with an inner diameter of only 5/1000th of an inch? They had to fly somebody from France to do this. And we were all pacing outside the room, the clean room, like expectant fathers because it was so hard. And the first fix didn't work because they sealed it shut, and the second fix did. Dan Harple had to do leak checks, countless leak checks. And the integration was very, very difficult. We had to keep track of all these 2,000 wires between the electronics and the hardware. There was about 600 meters or 2,000, it was very, very, lots of wires and very hard. We would break stuff while integrating. We had to stop to fix the brakes before going back to integrating, and then we kept breaking and we kept testing, and it was this continuous cycle of very, very compact work. We had fun too, and if you have time, go Google a video called Happy Birthday Curiosity, because we made Sam sing on the birthday of Curiosity on Mars. Sam will be running some great science experiments on Mars. We will be analyzing some soil samples. To make the soil samples go down, we had to program it to vibrate at various frequencies. When we're introducing a sample into SAM, it'll go through a resonance and it'll sound like this. To commemorate Sam's birthday and Curiosity's birthday on Mars, we decided to play a little song. If there's anyone listening on Mars, on this special occasion, you will hear this. So it probably is the first time that music was played on a planet. So Google Happy Birthday Curiosity and NASA, you'll see that. And Tom Nolan, my husband, was the programmer behind that music. SPRL, Space Physics Research Lab, was a partner in all this work. And Steve Patel and John Maurer were working very hard together with us. And this is and Ken Arnett and Ryan Miller as well. And of course, our very large group of NASA Goddard spaceflight engineers. We had a great team. These are all world-class engineers. John Maurer was a key person. He drew and maintained the gas processing diagram you saw earlier. He had the end-to-end vision of SAM electronics. He and Steve would have spirited discussions for 3 days. Steve called it their yell and tell sessions. They'll yell at each other for 2 days and then spend the 3rd day telling everybody the design. The GC, the gas chromatograph, was built by the French. There were cross-cultural communication issues. When the French team first came to Goddard to test, we sent the French team a handshaking signal to their electronics called no-op. This universally means a command to execute nothing and send us an acknowledged packet back to say, hey, we got your no-op. Instead, the GC team promptly shut down because they interpreted no-op as no operations, meaning stop operating. I didn't think to define no-op in our ICD. In all, SAM was a massive exercise in coordination, planning, troubleshooting, testing, more testing. We couldn't have done it without Paul Mahaffey, who guided the team and trusted the team members to deliver. I never felt I was alone in building SAM. I felt empowered by the management and had the guidance of Paul Mahaffey, John Maurer, Steve Patel. That didn't mean there wasn't any drama or stressed out engineers yelling at each other. We knew we had one shot to do this under a very hard planetary deadline. And if it meant coming in at 6:30 to test hardware or staying till 9 p.m., we did it. We all owned SAM. It was a challenge to work and build a team. Here's the installation of SAM onto Curiosity. And the slide of the rover inside the TVAC chamber. And that's me with Curiosity pre-launch at Cape Canaveral. The launch, November 26th on the Atlas V. And the first thumbnail. I was jumping up and down in that back room when I saw at JPL when I saw this shadow picture of the mast. And here is a picture of the happy team. And Paul Mahaffey is the PI. And was at the time the lab chief, and now the lab chief is Will Binkoff. In the 3 years that SAM and Curiosity have been on Mars, we've made significant discoveries. I want to point out that the bullets in yellow have SAM contributions. That's how important SAM is. We did find that Mars was once wet, warm, habitable. There was much, much more water on Mars than now. And the water was there over a long period. And we found multiple signatures that showed that there was a thicker atmosphere, like certainly the heavy isotopes remain. So there was an enrichment, and there were organic carbon found. And if you want more information, the results are on this website. So I want to talk about MAVEN. While working on SAM, we had to keep going and build another mass spectrometer called neutral gas ion mass spectrometer on the MAVEN spacecraft. As you know, MAVEN launched in November 2013 and is now orbiting Mars. The year of MAVEN's launch between January and August 2013, during pre-delivery testing, NGEMS suffered 3 intermittent resets. The first reset was after X-axis vibration in January 2013. The second reset was after we moved to Lockheed Martin for the spacecraft integration in March 2013. Eric Ryan and I and others mined the data and found out that we had a problem in the RF unit on NGEMS. After the second reset, I was very alarmed, and I told QA, this will come back and bite us if we don't fix it. But we couldn't do anything until we had a spare RF, and so while Mike Barciniak went on building the spare RF unit, the spacecraft work continued, and NGEMS was mounted on the spacecraft. We suffered a third reset in August 2013 after we moved to the Cape, and it was clear we either lived with this reset problem or we fixed it. After much deliberation, I was saying, fix it, fix it. In late September, we were given the go-ahead to work, and we removed our instrument from the spacecraft. The next day, October 1st, the fiscal dispute in Congress caused our government to shut down for 21 days. Because of the shutdown, we had to wait 3 days to get permission to enter center to finish the repair work. You understand, this is kind of late. We need to get this RF swap finished, get the job done during this 3 weeks, ship it back to the Cape for integration, and it's kind of close. We're launching in a month and a half or 2. So, well, we really did book. MAVEN launched on November 19, 2013, and this is the happy crowd. And some of us were I think we were so happy to just see this go. I have a side story to tell you. On January 2013, Siding Spring Observatory in Australia spotted a comet whose closest approach to Mars was about 138,000 kilometers, 86,000 miles, on October the 19th, 2014. And just 6 days prior to perihelion on the 25th of October, 2014, at a distance from the Sun of 1.38 AU. MAVEN entered Mars orbit September 22nd. So this comet was coming to us just after we entered Mars orbit. Back in 2001, I worked on Comet Nucleus Tour, Contour. And its primary objective was to fly through a bunch of comets. You know, Enki is one of them. Well, guess what? Contour blew up shortly after launch in July 2002. Now, the universe has delivered to us a comet which had traveled 1 million years to the very spot that MAVEN NGEMS would be. Same name too. I think this is karma. Contour blew up, we get a chance to fly through comet dust. Not many people get a second chance to do anything like that. NGEMS flew through the Martian aurora created by the comet incursion into Mars. We saw lots of energy deposited. And according to Medibena, NGEMS detected 12 to 14 types of metal ions, including sodium, magnesium, iron. These are the first direct measurements of composition of dust from an Oort cloud comet. I'm currently working on MOMA, an ESA ExoMars rover instrument, and we just completed EMI-EMC testing a couple weeks ago. In my 30 years at Goddard, I have learned it's good communications between scientists and engineers and technicians and teamwork that build successful instruments. The lab chiefs I served understood how to build successful instruments, and they assembled a kind of like a guild of engineering team members who build on the knowledge that were picked up over time. The mechanical, the electrical, the thermal, the materials, the contamination engineers, all these engineers, they had to work with each other. It's this cross-fertilization of knowledge that allow us to chase down every problem, and it is in the chasing down of every anomaly that, you know, behind, like, failure is not an option. That's a lot of hard work. A test and retest, dogged engineering to deliver the most robust design. And above all, the teamwork has to happen. The team has to trust each other. I like a quote from Captain Sully, the pilot who landed the plane on the Hudson. He said, "We need to try to do the right thing every time, to perform at our best, because we never know at what moment in our lives we'll be judged on." And I like to think that all our engineers should adopt this attitude. From bullock carts to rovers, from Malaysia to lactation rooms to Mars, I'm still amazed at how lucky I am to be here. I could never imagine I would be standing here before you today. I'm grateful for the opportunity and the freedom America has given to me as an immigrant and all the opportunities NASA has given me as an engineer. I'm grateful to my wonderful husband, my great children, my understanding and patient parents, my supportive siblings, for being there for me always, and to my numerous mentors who's helped me along my way. I always say that my parents and family and mentors have helped launch these mass spectrometers. America also embodies the ideals I have. Opportunities to many, its spirit of equality and acceptance for all. Together with these ideas, if we speak out, we collaborate, we listen, we can reach for the stars. And finally, this is a picture of the comet, and this is pictures of my family. That's all. Thank you. Questions?
Look, some of the folks hired recently for doing science are expressing some concerns dealing with engineers. Do you have any comments on how the perceived barriers between science and engineering might be addressed?
Okay, so Okay, so maybe I'm speaking, I've been here for 30 years. I believe to build good science instruments that you have to have good communications with the engineers. And I believe the only way you're going to get your good science instrument is to embed your engineers into a science directorate. And not only that, the whole learning of building electronics and building equipment for space development cannot be just a one-time engineers are fungible type thing. You have to have the engineers work directly with the scientists, understand the requirements, and then build on the knowledge that you pick up over time. It's like a guild. It's not like here I need a mechanical engineer to just build me this widget. It's more than that, because the requirements, no matter how perfect doors is, it's just not going to be written down one bullet at a time and then verified one bullet at a time. There has to be a give and take. And the other thing is, if engineers think that scientists are going to not change their minds, they're just because engineers, the scientists always change their mind. They always want more data. You need to understand the requirements and then build for that. The additional unknown. So I think communication and embedding the engineers, and then having this legacy of learning. You know, Steve Patel, I heard him say, he had 22,000 pages of notes, 20,000 pages of mistakes. Right? So my point is, you need to learn from your mistakes, and you need to embed the engineer with the scientist, and that's how it's going to work. The whole idea of trying to put an engineer and pull them from this pool works somewhat. I just think that it's very, for instruments especially, I speak from instrumentation, I really believe that you need that kind of deep knowledge of the requirements. Does it answer your question?
It expresses the same feelings I have about it. And also, of the 20,000 pages of mistakes that Steve speaks of, most of that is how he fixed the mistakes.
Correct. It's not 20,000 pages of mistakes. It's how he got to a good answer at the end.
Yes. So did your sister go to the science college in Malaysia also?
No, my sister did not go to the science college in Malaysia. It was just me.
And it was a boarding school?
It was a boarding school, and we could go home twice a year. The journey was pretty arduous because the school had buses to take us home, and the journey, because Malaysia had no developed roads, so we would go through these villages, and the bus would go through these very bumpy roads, and we'd share the road with chickens and goats and the occasional car and motorcycles, etc. And it always took a long time. We start very early in the morning, and by the time we got home, it's 8 at night. So about 12, 13 hours. And we had to stop to many villages to drop other kids off. So, and I was on the other side of Malaysia, so we took a long time. So twice a year, I would go home. And I see my parents for maybe 3 weeks, sometimes a month, every time. And that was how I grew up.
So I remember being a little girl in private school, but I was the only little black girl, and sometimes folks were not as welcoming, and here, in America. And then I remember growing, up and going to graduate school, and in my PhD class, I was the only woman, and sometimes even there, it was not the best. I kind of think that it seems like the tenacity and the grit that you need just to be able to be successful here at NASA is something that I think probably most people that work at NASA, but specifically I think women here do. And although I would never advocate for having a difficult childhood, I mean, how do you think that we can encourage the younger generations to kind of develop that tenacity and grit, because life is not always easy?
I think you tell stories. Because, kids actually listen. You think that they don't listen, but they do. Whatever you say to them, you think, oh, they just roll their eyes. I think kids do listen, and the only thing you can do is like my parents, right, they told us, look, we didn't earn enough. It's a struggle because it was so hard to clothe 4 kids and give them shoes and bring them up. And I think that my parents telling stories helped me understand where I came from and understand where I need to go. So the whole thing about the family plan, right? We were going to get on the family plan. The family plan was to get all 4 of us through college. The family plan was to make sure that we all had the funds to do it. And that was done because my parents told stories. And you know, they told stories, horrible stories about the war and how the Japanese had come in and really, you know, decimated whole villages. Like it depends on which village you're in. If you're in the one higher than, you know, the river, upriver, you're safe. If not, you're not, you know, the whole village is, you know, completely killed. So I think I learned very, very early to really count my blessings. And it was always the cup is half full. So some people cannot take the pressure, right? Because at some point you break. So you try not to do that. So telling stories, I think, is what you have to do to encourage kids, in my opinion. Yes, anyone else?
Okay, very good. That's fantastic.
Thank you.